Welcome to Brain Vision.
16.22. So we have a wave on a string. Its speed is 40 centimeters per second. At a position of x equals 10 centimeters, we have this form for the displacements. We're told the linear density of the string, and so we want to find frequency and wavelength. And then if the general form for any point on the string is, we're used to seeing, then we want to find all of these things. So the amplitude, the wave number, angular frequency, and whether we need a plus or minus here. And then we'd also like to find the tension in the string. So F is equal to omega over 2 pi. We can see right here that omega is just 4 radians per second, because the omega t part here is not been changed. The kx we'll have to think about a little bit in a moment, because we just have a 1 here. So we got to figure out how that works, but for right now, omega is just 4 radians per second. And so the frequency that corresponds to is 0.64 hertz. So it's pretty low frequency. Now this so 1 is equal to k times our position. So we're told that k times 10 centimeters is equal to 1. And this implies that k is 0.1 radians per meter. I'm sorry, radians per centimeter. Now the wavelength is 2 pi over the wave number. And so it's 63 centimeters. So just comparing this with this now, we see that 5 centimeters is the amplitude. We already found that the wave number that would go in here, based on this, is 1/10 radians per centimeter. Centimeter. The angular frequency also is 4 radians per second, just matching up the variables names in here with what appears in the expression we're given. F here, we have a negative sign. Omega is generally considered to be positive. There's not really many uses for negative frequencies, this sort of thing at least. So it's negative, and so the wave is traveling in the positive x direction. And so the speed which we're given is equal to the square root of the tension, which we'd like to know, divided by the linear density, which we already know. So the tension is going to equal the speed squared divided by the density. And this works out to be 0.064 newtons.